All right, welcome to chapter 6. In this chapter, we're going to talk about atmospheric moisture, stability, and various kinds of clouds. And so with this chapter, we're starting a new sphere. We're still going to stick with the atmosphere, but we're also going to talk about the hydrosphere, which is part of the Earth that contains water. And without water, we would not have many of our amazing clouds that we have in whether we're talking about storms, as you can see up here in the upper part of the uh, slide, we have the tallest kinds of clouds, cumulonimbus clouds, or down here with hurricanes. And hurricanes and its clouds are one of the best examples of the power of water within our atmosphere. So with this kind of discussion with the mixture of the atmosphere and water, we're going to talk about water vapor, which is just the gas form of water in the atmosphere. We're going to talk about humidity and various kinds of humidity, absolute, relative humidity, dew point temperature, which is something that you may have heard of before but don't quite understand, and other types of topics like buoyancy, stability, get into various kinds of fog, clouds, and then something called orographic, which essentially is just clouds that are there due to mountains or other topographic barriers. So let's talk about water. And we can talk about water with the hydrologic cycle. Now the hydrologic cycle is essentially precipitation, then that precipitation runs off into the ocean, and then there's evaporation, and then after evaporation, once it's high enough in the atmosphere, we have condensation. So with that, we have water and the three states of water that occur naturally in our atmosphere. Water vapor, we have ice, and then we have liquid water. Now, I want to focus on just the atmospheric water vapor and liquid water. We're gonna ignore ice for now. With water vapor and liquid water, there's energy that's actually stored when we change a phase. If we go from water to water vapor, that's basically evaporation. And evaporation requires energy from the environment. So anytime you have evaporation, you are cooling down that environment. So you can think of when you have, let's say, sweat on your skin or water on your skin, and you feel a nice cool breeze, you tend to, well, feel colder because evaporation will cool your body down. On the flip side, if you go from water vapor to liquid water, condensation, that actually releases energy. And that sort of heat, that energy, is fuel for thunderstorms and hurricanes that we're going to talk about in chapter 7. So let's talk a little bit more about water vapor. Humidity, at least absolute humidity, is really just the actual amount of water vapor in the air or per volume of air. And one thing I want you to really remember is that higher air temperatures have a greater ability or capacity to quote unquote hold water vapor. It doesn't really hold it, but it just has, I like to use that analogy to get the point across that higher air temperatures allow more evaporation and therefore have a greater chance of having water vapor. Now, relative humidity. Relative humidity does not actually tell us how much water vapor there is in the air, What it does is it takes the amount of water vapor in the air, compares it to the amount that could be in that air, and it gives us a ratio. So it just tells us how close we are to the maximum amount of water vapor in that air. It's usually written out as a percent, where 100% means that we have reached our maximum capacity, or in other words, saturation. Saturation. Because remember, higher air temperatures mean that we increase the amount that could be in the air. So if we have higher air temperatures, that means we actually have to have higher actual amounts of water vapor in order to reach 100% relative humidity. So on the flip side, if we cool the air down, then we have a greater chance of getting saturation. So because this can lead to clouds, let's talk about how we can increase relative humidity. I like to break it down into 3 different ways. You can actually increase the water vapor in the air, which doesn't affect temperature. We're just talking about actual increases of water vapor, the gas form of water. We could also decrease the temperature, cool the air down, because remember, lower air temperatures don't have a great ability to keep water vapor, so it usually has to turn it into liquid water. That's the most common way of increasing relative humidity, is to cool that air down. Or we can do both. We can increase the water vapor and decrease the temperature. In reality, and we're going to use a graphical example here, most of the time we increase the relative humidity by decreasing temperature. So for example, let's say it's 5 p.m. This hollow black circle represents the capacity of water vapor in that air, and it's bigger because at 5 p.m. our temperatures are usually higher. But the blue circle represents the actual water vapor. So if you compare the sizes, it's roughly about 20%. Now let's move on to 11 p.m., where the water vapor stays the same, but the temperature has cooled down. So if the temperature has cooled down, then our capacity has lowered, and that gives us maybe about a 50% relative humidity. Let's cool the air temperatures down even more. Let's say it's 5 a.m., and you can see that the water vapor, the blue circle, is the same size as the black circle, so we have reached a 100% relative humidity. And this is where you can get dew that forms outside. So sometimes, especially in the cooler months of the year, you might go outside early in the morning and find dew on the ground, or on your car at least. If it's below freezing, you would find frost. We've reached saturation, and no longer can we have water in the gas form. So that temperature that we must cool air down to, in order to get a relative humidity of 100%, is called the dew point temperature. And when that occurs, we can get various forms of solid and liquid, mainly liquid because we live in California, but sometimes solid. We can get clouds up in the air, we can get dew, we can get fog, and if we're really lucky, we can get rain or snow in the cooler, let's say up in the mountains of California. Another example of the dew point temperature is that, let's say you have a nice glass of ice water, and it's somewhat humid outside, and you set that glass down on a table, and you might notice after a little bit of time that water is forming on the outside of that glass. Well, that glass has cooled the air around the glass to the dew point temperature, and you have water forming. And that water is not coming from inside the glass, let's hope. The water is coming from outside of the glass. And if you don't put a coaster down, then you may actually ruin whatever you've put the glass down onto. Sometimes in the real world, we can see billowing fog due to air moving into cooler air, mixing, and reaching the dew point temperature and creating fog. So let's go, since we're talking about clouds, at least eventually toward the end of this chapter, how do clouds form higher up in the atmosphere? And how do we get water that typically is found at the surface up into the atmosphere? Before we talk about that, we have to think about buoyancy. And think about how hot air balloons work. When you have a hot air balloon, you have a heat source, and that heat source increases the temperature inside the balloon, and then that balloon, because air is less dense when it's warm, will start to rise. So when you have air that's less dense, aka warmer in this case, it wants to go up. So we think about gravity that likes to keep a lot of our molecules close to the surface of the Earth. But if we have warm air, if we have air that's warmer than the air around it, it'll actually want to go up, and we call that a buoyancy force. So think of a bubble of air, kind of like a balloon, as an air parcel, as I've highlighted right here. That air parcel has two forces that are acting upon it in a vertical sense. We have gravity that wants to keep the air parcel down, and buoyancy wants to, if it's warmer or if it's less dense, wants it to go up. So higher density parcels, which are cooler air, they want to stay down toward the surface of the Earth. But lower density or warmer air, they want to go up. And when air parcels go up, because there's less pressure as we go up, the air parcels actually expand as they go up. And when they expand, they cool down. But they don't cool down because they mix with the air around it. Believe it or not, air parcels tend to move up. So right here I have a diagram showing air parcels that are rising and they're expanding because there's less air pressure. Anytime you have air that expands, it cools down, and it cools down adiabatically. That rate of cooling, if we're not talking about clouds, just talking about dry air, is about 10 degrees Celsius per 1,000 meters. And we can even say the same thing about air parcels that go downward. They compress and warm up. In fact, air parcels that compress and warm up is the root of why Santa Ana winds bring us such warm air. Now imagine an air parcel going up and it's expanding, it's cooling down. What's going to happen to that air parcel? Eventually, it's going to cool down. If it continues to rise, it's going to cool down to its dew point temperature. And when it reaches the dew point temperature, relative humidity is 100%, and we can get a cloud. Now, sometimes we want to assess the possibility of air rising. And what we have to do is we have to look at the rates of cooling within a parcel, which, by the way, inside a parcel is 10 degrees Celsius per 1,000 meters. If it already had, let's say it's already a cloud, then it's at a rate of 6 degrees Celsius per 1,000 meters. So we have those two rates. but we have to figure out how the environment around those parcels are cooling. And this is where it can get kind of tricky. So I'm only going to just briefly talk about this slide. Normally I would use some math to show you, but I have a couple of videos on Canvas that might help you understand this, this technique that we use to assess stability. Essentially though, if the environment is cooling at a rate that is less than 6, we say the air is stable. Stable air doesn't really want parcels to rise. So we tend to get clear sunny days when it's stable outside. On the other hand, if the environment is cooling at a rate of greater than 10 degrees Celsius per 1,000 meters, then we have unstable air. Unstable air tends to create not just clouds, but very tall clouds, and in the extreme cases, thunderstorms. And so that's the gist for this slide. Here's another way of looking at it. Cloud patterns that we see are visual markers of stability. If we have unstable air, then we get updrafts, vertical clouds, and we get a cloud that looks like this, which is one type of cumulonimbus clouds. Stable air tends to not even create clouds, but if it does, those clouds tend to be horizontally developed. So they may be stratus clouds. If you get any kind of precipitation out of it, it might be drizzle. Versus unstable with your cumuliform, cumulonimbus clouds, you might get heavier showers and thunderstorms. So to boil this down to in terms of stability, unstable air wants to rise until it's stable again. If it rises up to the point where relative humidity is 100%, we can get a cloud. Stable air doesn't like vertical movement and tends to lead to clear sunny days, which is typical of what we find here in Southern California, especially in the summertime. So now let's turn our attention to clouds. We've talked about how water vapor can turn into liquid form. And by the way, clouds are basically suspended liquid water droplets. And we talked about how we can get water up into the air through stability or unstable conditions to even create these clouds. But there are various kinds of clouds, and we typically classify clouds based off of two criteria. We have form and altitude. And we don't have time to go through all the important or basic cloud types, but I do want to talk about what cirrus clouds are, which are these thin, wispy, feather-like clouds high up in the atmosphere. We have stratus clouds, which are typical of June gloom type of clouds. And then we have our cumulus form clouds that are puffy, and if they're very tall, we can get something called a cumulonimbus cloud, which we'll talk about in a second. Nimb is a prefix for precipitation. So nimbostratus, as you see down here, is a type of low-level cloud that actually can produce rain. So that was sort of the shape of clouds. Going into the type of clouds based on height, we have low clouds, which include your nimbostratus, your cumulus, your stratus, maybe stratocumulus. Middle level clouds, altocumulus, altostratus. And then your high level clouds like cirrocumulus, cirrostratus, and cirrus, the wispy kind of clouds. And then you have the one kind of cloud that is my favorite cloud that goes all the way to the top of the troposphere, at least it can. So it extends from the lower part of the troposphere to the upper part of the troposphere. And we call that a cumulonimbus cloud. So within a cumulonimbus cloud, lots of different things can happen. We can get a thunderstorm. Basically, thunderstorms are born out of cumulonimbus clouds. We also get a mixture of ice and water, and that can create a lot of heavy rain and even hail. And this is a picture over here of a cumulonimbus cloud from above. Once it hits the top of the troposphere, it tends to flatten out because it can't get into the stratosphere usually. Sometimes it can, but not usually. Okay, so what is fog? Fog generally is just a cloud on the ground. And there are two basic kinds of fog that we're going to discuss in this chapter. Advection fog, as you can see here, is a type of fog that really is very common around the Golden Gate Bridge and along the coast of California. Advection fog means that the fog has formed in one place and has moved horizontally onto another place. So this fog has formed over the ocean and then moved inland over into San Francisco and has created extreme visibility issues. And actually fog can be very troubling when it comes to traveling and any kind of transportation. Radiation fog. Now, radiation fog is the kind of fog that doesn't move, but forms because at night, long-wave radiation wants to escape, especially on a clear winter night. Long-wave radiation escapes towards space, cools the air down, and if it cools it down to the dew point temperature, you get fog. So we're looking at the Central Valley of California, and we have lots of different fog around the middle part of this valley. Sometimes that fog is called Thule fog, and it can actually create very low visibilities. So in addition to air rising and creating clouds due to convection, now convection was the lifting mechanism that we talked about when we're talking about stability and unstable air. We talked about air rising in a low pressure system back in chapter 5. We call that convergent lifting. So we want to talk about two other ways that the atmosphere can actually lift or go up to create clouds. What's very common in California, whether we're talking about summertime thunderstorms or even the wintertime rain that we get so much in the mountainous areas, we have something called orographic. So air, when it hits a mountain, it wants to go up. And when it goes up, it helps create more clouds and more precipitation. Front is a massive cold air that meets up let's say a massive cold air that actually is plunging toward another mass of warm air. Since we know that cold air is more dense, it forces that warm air to rise, and if there's moisture in there, it'll rise, create clouds, and sometimes even cumulonimbus clouds. So let's talk about those last two in a little bit. So orographic precipitation, what happens is not only do clouds develop over mountains, but we have one side of the mountain that tends to be much wetter. So the windward side over here is the side that creates the clouds and also can create much more precipitation. On the other side of the mountain, when air descends, it warms up adiabatically and it dries out. So we tend to not see very much rain on the rain shadow on the opposite side of that mountain. Sometimes we call that the leeward side. And we see a lot less vegetation also because there's not as much precipitation. And I like this picture down here at the bottom right because it shows the effect of mountains that the mountains have on creating clouds. On one side of that mountain, we tend to get more clouds versus the other side. And those clouds, regardless of what side, tend to be even taller. Going back to frontal lifting. Now, we have something called an air mass. Air masses are just large pieces of air that tend to move toward the mid-latitudes. So right about here, we have cold air and warm air that want to clash or meet up. Because there's a lot of mountains in the western part of our country, the primary area where we see air masses clash is really in the middle part of our country, right about there. So what happens is that cold air coming from Canada will meet up with warm air coming from, let's say, the Gulf of Mexico. It forces that warm air to rise dramatically. And the more of a vertical sense that we can get of that cloud formation, the better the chance we get our cumulonimbus clouds and our thunderstorms. Here's a dramatic example of cumulonimbus clouds being formed due to a cold front. So that cold front that we just talked about is about right here, and it's forcing air upward. Almost looks like a cliff covered in snow, but these are actually clouds being abruptly lifted by a cold front. And a squall line is a line of thunderstorms. And we're going to talk a lot about thunderstorms and then tornadoes and hurricanes in the next chapter, chapter 7.